Okay, here we go. We should be all sorted out and ready to go here. Here is going to be our first problem. You can see it says an airplane takes off from DIA, travels 430 miles due north before the pilot realizes the plane is off course. To correct the flight pattern, the plane travels 310 miles due east before changing direction to the correct flight path. How far is the plane from the airport, and what is its heading in degrees north of east when the pilot finally gets the plane on course? Use only a protractor and a ruler. Okay, for this problem, we are going to learn how to do vector addition. Now, there are going to be two methods that we use for vector addition. Wait, we can do it. Two methods that we use for vector addition. The first one, which we'll learn in this video, is a method that is what I call the two-scale diagram method. And the second method is what we call the algebraic way. I often call it the mathy way. So you can either do it with a picture with a two-scale diagram, or you can do it mathy with algebra. We're going to start by learning how to do it with a two-scale diagram. Now here's a caveat, is that drawing on my little guy here and drawing a two-scale diagram is actually like really super incredibly hard, because you need these tools. You're going to need a ruler, you're going to need a protractor, and finally, you're going to need graph paper. If you can see here, it's nearly impossible to get graph paper on my little screen here, and what I have to do is I have to draw on this ruler on this thing, and then it shows up on there. So like knowing where I'm putting my pen is really, really hard to get really accurate lines. So I will do my best, but that's my caveat, is that I don't really know how well this is going to go here. Okay, here's what we're going to do. To draw a two-scale diagram, we are literally going to recreate this problem on our papers, on a piece of graph paper. So right now, you have out a piece of graph paper in front of you, you have a ruler, and you have a little protractor right here. We're going to start by drawing our axes to define our problem. Now, here's what I'm thinking. Whenever you do one of these kinds of problems, you want the problem to take up the whole sheet of paper or the whole space. Not like a little teeny tiny corner. We're not going to draw them small. We're going to draw them enormous. As much space as you can take up on the paper, that's how much space you should be taking up. So I'm going to start by drawing this, and the first thing that I'm going to do is I'm going to draw my axes, and I'm going to figure out where I really want my axes to go. So I have an airplane that takes off from DIA, and it travels 430 miles north, and then it travels 310 miles east. When I'm looking at my little axes here, this is like north, south, east, west. When I'm looking at my axes here, if this little guy starts going north and then ends up going east like this, then I'm thinking I'm going to be spending most of my time in this first quadrant here. So I'm going to draw my first quadrant so that my first quadrant takes up most of my paper. Okay, now here we go. This is going to be the very, very tricky part where I try to draw the axes, and you say that's not that hard, Miss Wilson, but it actually like really for serious is. Okay, so I'm going to start right there. That's where I'm going to start. Okay. Now when I draw the axes, how far does that go? Okay, that's not too bad. When I draw my axes, I am going to draw them so that they are perfectly straight, which means you will need to employ a ruler in this part of the program as you try to draw your lines nice and straight. This is also part of why it's a great idea to have graph paper. Okay, here we go. Nice and straight line. So far, so good. Okay, here's what you're going to do next is you're going to label your axes. I'm going to label this guy at the top, north. Down here at the bottom, I shall label this south. Here I shall label this east, and I shall label this end west, because that's the way that a compass goes. Now, here I've labeled everything north, south, east, and west. But if the problem didn't give me north, south, east, and west, if the problem gave me something like, I don't know, up and down and left and right, then I wouldn't call it north, south, east, and west. I would call it whatever the problem calls it. So you have to be careful when you label your axes to label your axes with whatever corresponds to the problem. That on your test is worth a point. You get a point for labeling your axes. Next, and this is the trickiest part of the whole thing, the next part is to choose a scale. Now, when you choose a scale, you want a scale that's going to make it so that your diagram takes up almost the whole page. And by that I mean that it has to be at least more than half of the page. When I'm looking at this, I'm saying, okay, this thing is going to go 430 miles. Now, I'm drawing this exact scenario on my page, but you know what I'm not going to draw is I'm not going to draw 430 miles because my screen is not 430 miles big and your piece of paper is not 430 miles big. So instead, we're going to create a scale so that we can scale it down a little bit. Now, here is the tricky part. The hardest part is finding a scale, and this is going to be like incredibly super challenging for me because I am on not a real piece of paper. Yeah. Okay, I kind of see what I have to work with here. Okay, so here's what you're going to do. I like to start by choosing a scale that feels really reasonable. Something that feels reasonable here would be that 1 centimeter is equal to 100 miles. So 1 centimeter on your paper is equal to 100 miles in the problem. That feels like a pretty reasonable scale. If I used 1 centimeter is equal to 100 miles, that would mean that I need enough space to have 4.3 centimeters worth of space here on this axis, which I do have at least, let's see, that's my 0. Oh gosh. Okay, see again, I told you this was going to be the hardest part. Okay, there's my 0. So I have at least 4.3 centimeters worth of space. Okay, I do, but that's getting kind of tight for me. And that's definitely taking up more than half my page. For you, on your sheet of paper, 4.3 centimeters is probably taking up way less than half your page. So what I would do if this wasn't good enough is I would double it. I would say, okay, let's try 2 centimeters is equal to 100 miles. If you try 2 centimeters is equal to 100 miles, now, instead of needing 4.3 centimeters north, you now need double that. You need 8.6 centimeters north. So check and see on your paper, if you use your ruler, do you have enough space to fit 8.6 centimeters on that part of your paper? If it fits, but it's still not taking up more than half your page, I would double it again. This time, let's say you go with 4 centimeters is equal to 100 miles. If you use 4 centimeters, then before what took you 8.6 centimeters will now take you 17.2 centimeters of space. Now, at this point, this should probably be a pretty good scale for you, where you see, okay, yes, I definitely have enough room for 17.2 centimeters, but also it's big enough that it's going to be taking up my whole space. That's how you choose a scale. It's the hardest part. Once you choose a scale, you are going to write your scale on the top of your paper. Writing your scale is worth a point, so write it somewhere on your page. I am going to use 1 centimeter equals 100 miles, so I'm going to erase these other scales because these are not the scales that I'm going to be using. You write down the scale that you are using on your piece of paper. 1 second, please, as I erase. Yeah. Okay, sorry, it's super laggy today. We're just really taking our precious time. Okay, after you have written your scale, now the next step is to draw your vectors. I'm going to draw my vectors in a different color. For my first vector, I'm going to choose green. Well, I was going to choose green. Sorry, we really are just really crazy, super laggy today. Okay. Green it is. Here we go. Okay. Check it out. We have an airplane that takes off from DIA and it travels 430 miles north. That's my first vector. It travels 430 miles north. That's the very first displacement. To draw our vectors, I always draw my vectors exactly the way that the actual thing went. So it started at DIA and went 430 miles north. I'm going to choose my starting point as the origin. But here in the problem, it clearly says that the plane starts at DIA. So I'm going to label the origin, which is my starting point, as DIA. Just like this. Now, the plane goes 430 miles north of DIA. I'm going to draw 430 miles north of DIA. Hang on, this is going to be very, very challenging for me. When I draw it, I'm going to draw 4.3 centimeters north of DIA. How many centimeters are you going to draw? Well, if you want to figure it out based on your scale, what you're going to do is you're going to take the number here, 430. You're going to divide by this side of your scale, the side that says 100 miles. Then you're going to multiply by whatever you get on this side of your scale. So if you have 4 centimeters here, you're going to take 430. You divide it by 100, that gives you 4.3. You multiply by 4, that gives you 17.2. And then you know how long to draw your little vector. So I am going to start at DIA here. Am I on the line? Oh gosh, see, this is what I told you. It's going to be so nearly impossible. I don't even know if I can do it truly. Okay. I'm going to start here. Am I on? Nope, I'm not. I'm too high. At this point, you've already drawn your picture, and it's beautiful and perfect. Okay, let's see. Am I on here? Okay. And then I'm going to go up 4.3 centimeters right there. And that's where I'm going to stop. Okay. Now, if you're drawing on a piece of paper and you're using pencil, please make sure to make this line super nice and dark here so that I know for sure. I'm using a different color, which makes it easier, but please make sure. Oh gosh, I should stop touching stuff. Don't touch stuff, Miss Wilson. Okay, sorry. I got the evil working sign, which sometimes means that it won't work. Okay, great. Whenever it says working, I'm like, that is just not a good sign. You should not be working. This should be easy for you. Okay, next. What you're going to do is at the very end here, you are going to label your vector with a little arrow showing the direction of your vector. One of the more common test mistakes that students will make is students will forget to draw an arrow on the end here, but because it's a vector, it has direction, and so you need to represent that direction with an arrow. The next thing that we're going to do is we are going to label our vector A, and I'm going to teach you a few conventions for writing vectors. Hang on, let me erase this here really quick. Bye, sorry. Oh gosh. It's only taking me 5 years to erase stuff. But that's okay because you guys are super patient people, which I super appreciate. Also, let's see, wait, we're almost done. Also, you're kind and considerate. All good things to be. Okay. Okay, great. So, when we write the vector A, here's how we write. Oh gosh, I already gave away what it is. We're going to call this first vector A. We normally like to call vectors by letters. And so we're going to call this first vector A because it's the first one. So we call the first one A. And you know what we'll probably call the second one? B. And if we had to give a guess for what we'd call a third one, we'd probably call a third one C. And I think you're getting the gist. So to write vector A, here's how we write vector A. We say that A is equal to 430 miles. But because it's a vector, we can't just write the number with the units. We also need to write the direction, and the direction in this case is north. Now, here's something that could be very confusing, is that this capital letter N, which stands for north, looks a lot like a capital letter N. And capital letter N in physics stands for newtons. And so to show that this means north and not newtons, we take this little direction here and we put it in brackets like so. And the brackets show, hey, this isn't units. We're not saying 430 miles newtons. We're saying 430 miles north. Then, to show that this little symbol is a vector here, we put a little hat on it like this, and we call this a vector hat. The vector hat is sort of like a little half arrow. So it shows, hey, this little guy has direction here, and the direction is listed over here. The direction is north. If you wanted to show vector A, you would write vector A with a vector hat is equal to number, units, and direction. All of those things are needed whenever you write a vector. If I wanted to talk about just the magnitude of A and I didn't care about the direction, to write A as a scalar, I would just write A is equal to 430 miles, just like that. But because we're looking at A as a vector, then we are going to use this notation. When I go back over here, I'm going to label this as vector A. And I'm going to do it right next to this line so that I know that this is what I'm talking about when I talk about vector A. So, vector A is equal to, wait, you can do it. Please load. Okay. 430 miles north. Okay, and that's the first part. Next, we need to draw our second vector. So now I'm going to choose a new color. We shall call this vector, vector B. Very creatively. Now, the plane travels 310 miles due east. That is vector B. When we draw vector B, we always draw our vectors the way that it actually happened. In other words, the way that the plane actually experienced this flight path. Now, here's a crazy mistake that some students make that will lose you tons of points because you'll get all lost and confused and you won't know what to do next. The plane started at DIA. It went up to here. Then did the plane go back to DIA and then start going east? No, you say, that's ridiculous. The plane went from DIA up to here, and then at that point, the plane then traveled this way. When we add vectors together, we always draw them tip to tail, which means the tip of my first vector is where the tail of my second vector begins. Draw it the way that you would draw it if you were actually the plane following this path. Okay, so here we go. So here, and this is going to be the hardest part for me, but this part is going to be easy for you, is actually just putting my pen down in the right place. Okay, that's kind of, wait, not quite there. Is that where I want it? Yes, okay. Now, the next step is to measure exactly how far you want vector B to go. We'll look at your scale again. You divide by this number and multiply by this number. If vector B is 310 miles, you can divide by 100. That gets you 3.1. Multiply by this number. For me, it's 1, so that gives me 3.1 centimeters. For you, this might be 4. Multiplying by 4 would give you 12.4 centimeters. Then we're going to draw from here. Am I nailing it right now? Okay, we're going to draw from here. And we're going to draw over, I'm going to draw 3.1 centimeters to right here. With your ruler, of course. Then please draw an arrow on the end of this guy right here to show that that is the direction that your vector is going. My arrow is bad, so I will fix it. Now you might think that this is a very nitpicky thing, but when you draw your arrows, please make sure that your arrows end right, that they're just very, very connected to your line. And here's why. If you draw a vector that looks like this, how do I know if this right here is the end of your vector, or if this right here is the end of your vector? There's no way to tell. So make sure that none of your little vectors here are decapitated. Please make sure that they are connected to that the arrow tip is connected to the body of the arrow. Otherwise, that's like extremely uncomfortable, and it's just hard to know where you really want things to be. So please make sure that your arrows are written clearly and make sure that they are connected. Okay. Next, we shall label vector B. Now at this point, you are very good at labeling vectors. So you would say, okay, this is vector B. Vector B with a vector hat, of course, because it is a vector, is 310 miles in the east direction. And there you go. Now, the final question, what we were doing all of this work to show, is to answer this question. How far is the plane from the airport? Wait, red, okay. Gosh, guys, this is like for seriously so crazy laggy. How far is the plane from the airport? That was a very bad line, and I don't want to redo it because that's a waste of time, but I am so perfectionistic sometimes, and so it just has to actually underline the word airport. Okay, how far is the plane from the airport, and what is its heading in degrees north of east when the pilot finally gets the plane on course? The final question that we're answering is where does the plane end up? In other words, what is the plane's displacement? Well, the plane ends up right here. Agreed? Well, all you have to do to find out how far the plane is from the airport is to measure how far is the plane from the airport. So here is what you will do. You will take your ruler and you will line it up perfectly to draw a little line connecting your starting point, which I will put right there. Wait, is this right? It's right. Whoa, okay. Right there is my starting. Oh gosh, I can do it. I can do it. Okay, right there, good enough. Right there is my starting point, and my ending point is going to be right here. Okay, we're gonna see how this goes. This is really, truly like the hardest part of this whole task for me. It's gonna be this part right here. Okay. Can't you do it? I really, truly don't know. Okay, so you're going to draw a line connecting those two things. Ah, I missed. Wait, oh, gosh, no, I didn't. That was perfect. Wow, this is so exciting. I can't even tell you how hard that was. Oh my gosh, I'm sweating a little bit. Are you sweating? Oh, wow, that was amazing. Okay, so now what you're going to do is you're going to draw a vector that starts at DIA and goes all the way to the end. And then you're going to draw a little arrow on the end. If we call this vector A and this vector B, then we would call this vector R. Yes, very logical. The reason why we call this vector R is because R stands for resultant. It's the resultant vector that results when you add together A and B. If we had another vector from there, if it said, then after the plane went 430 miles north and 310 miles east, then it continued on, and this time it went 317 miles north before turning and going 12 miles south. So if you had an extra vector that was an extra part of the plane's path, we would call that C. But do you see how vector R here isn't a part of the plane's path? It's the resultant of when you add up the parts of the plane's path. So we call this vector R. When we look at vector R, we are going to try to find the length of vector R and also the direction of vector R. To do this, all that you have to do is take your little ruler, hold it up to your little vector R there, which I will do on my paper, except that you can't see me doing it here. I will do that here, and then I will measure the length from this point all the way up to this point here. And when I measure that, it comes out right on my ruler to be about 5.4 centimeters. Now, 5.4 centimeters is actually not my final answer here because the plane isn't 5.4 centimeters away from DIA, so I have to convert that back into miles. To convert it back into miles, I undo what I normally do. So what I'm going to do is I'm going to divide by this side and multiply by this side. So I divide 5.4 centimeters by 1, and I get 5.4 centimeters. Then I multiply 5.4 centimeters by 100, and I get 540 miles. So I'm going to write here that R is equal to 540 miles. But that's not all. This is a vector, people. So now I need to also include direction. The way that I include direction is I use my protractor. Now, here's the thing, is that we could just say that the direction is northeast. Do you agree that the plane is somewhere northeast of DIA? However, if you just said northeast, that wouldn't be specific enough. Because isn't this point over here also northeast? And isn't this point over here also northeast? And isn't this point right here also northeast? All of those little points are all northeast. But the question is this the right one? Or is this the right one? Or is this the right one? And none of those are specific enough. So to tell where exactly this little airplane is, we are going to have to use our protractor. When we use our protractor, we are going to measure. Seriously, did that not catch that last one? Erase, please. Go away. You may vanish now. Yes, perfect. Okay, we're going to measure our angle. This says what is its heading. That means the angle or its direction in degrees north of east. When we measure in degrees north of east, that is telling us which angle to measure. Do you agree? There are two angles that we could possibly measure here. We could measure this angle here, or we could measure this angle here. This asks us for the heading or the direction in degrees north of east. What north of east means is north of east means that you start at east and then you start moving towards the north axis. So if I start at east and I go north of east, then I start at east and I click, 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 up until I get to the vector here. If it asked me for the heading in degrees east of north, that would mean that I start at north and I go to the east of that. So I start at north and then I head my way towards the east axis. So it would mean I start here and I go click, 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 until I run into vector r. That is how you know which angle to measure. It's which one you're carving out as you go either north of east or east of north. In this case, the problem asks us to find the angle in degrees north of east. So we're going to start at the east axis here and measure up to our vector r, which means we don't need this angle that starts here north and goes down to the east. We're looking for the angle in degrees north of east. We're going to call this angle theta. Now what you're going to do is you're going to take your protractor and you are going to measure on your piece of paper what that angle is. So you're going to line up the bottom of your protractor here. The little hole goes right on the origin. You'll line up this little line here. If you have a hole, then your hole goes on the origin. Some people don't. You'll line up the bottom line goes on your east-west axis, on your x-axis, and then make sure that this little 90 mark here is hitting the y-axis, hitting north. So you'll set that on your paper here, and you're going to measure the angle between here and here. And when I measure that angle on my protractor, oh gosh, don't click too much. Okay, sorry everyone. When I measure this angle on my protractor from here up until here, I get on my protractor that is just about 56 degrees for me, but it might be something different for you. So write down what it is for you. So I write down that this is 56 degrees, and I'll label theta here. Oh gosh, wait, I did a bad job. I did very bad. Erase. Sorry we got so much lagginess here today, people. You're like, you've already talked about that 7 million times. I know, it's just so annoying. Okay, 56 degrees. And finally, we're going to label the direction as well so we know which angle we're referring to. This is 56 degrees north of east, starting at the east axis and going north. And this guy right here, is our final answer. That is how you do one of these problems with a picture. If this question were on a test, the things that I would be looking for vector A drawn correctly with an arrow on the end, labeled correctly. Vector B drawn correctly with an arrow on the end, labeled correctly. Vector R drawn correctly with an arrow on the end, labeled correctly. I'd be looking for this number, 56 degrees right here. I'd be looking for theta to be labeled. I'd be looking, are your axes labeled? I'd be looking, did you write down what your scale is? I'd be looking in your final answer, did you get the right number here? Did you get the right number here? Did you get your directions right? And then finally, I would check your sig figs. For these, we're just going to match the sig figs of the problem. So here I have 2 sig figs, 2 sig figs. So here you see I have 2 sig figs, 2 sig figs, and we are all good to go. That is the first problem. We're now going to go ahead and try working on a second practice problem. Let's go ahead and take a look. actually, I'm going to try to quick pause the video and see if I can't clear out any of these tabs and maybe see if I can make it. I know it doesn't look like I have that many tabs here, but guess what? I have a whole other set of Google tabs that are hiding. So I'm going to see if we can try to fix any of the lagginess just a little bit. Let me try that really quick, and then I'll come back to you. One moment. Guys, plot twist. I literally thought I had like a gazillion other tabs open, and I actually do not. It's literally just that slow. Oh gosh, it's awful. Okay, here we go. A monkey leaves his favorite tree and he walks 62 miles due east and then 40. Oh, whoa, did I say miles? That would be a very long journey for a monkey. Okay, he walks 62 meters due east and then 45 meters due south to reach his favorite lunch spot. What is the displacement, both distance and the direction, with respect to due east from the base of his tree to his lunch? Okay, let's go ahead and start by figuring out which of our axes we would like to primarily consume the page. Okay. Once again, we got a north, south, east, west type situation. We got a little monkey sitting at his favorite tree, then he goes east, and from there, after he goes east, he's going to walk south. So I'm thinking we're primarily going to want to be working here in this fourth quadrant. When I draw my axes, then I'm going to draw... Okay, let's see, where is that leading? Oh no, don't do that, please. Okay, we're going to start here. I think it's going to be perfect. And I'm going to draw a line straight down. Yes, lovely, except that was just like a little bit slightly too long, but I think we're going to be okay. I think everyone's going to make it. Okay, next, I'm going to draw this other line here-ish. I think it's going to be pretty perfect. Does that work? I'm going to go a little bit lower, actually. Does that work? Okay. I think that's going to work for us. We'll start here. And we'll go across like this. Okay, yay. Okay, here we go. We're going to call this north. We're going to call this east. We're going to call this west. Maybe. We're going to call this west. That was the worst W I've ever written. I cannot justify that W staying and living here on this document. No, no, no. Try again. West. And then we're going to call this down here south. Okay. Now, we shall choose a scale. This, again, is the hardest part. I'm going to choose something that works for me. You choose something that works for you. When I look at my little piece of paper here, except it's not a piece of paper, it's a screen, I'm thinking that I should be able to fit, oh gosh, this might be tight, might be very tight, people. Okay, let's see, can I go from here, and can I go down 6.2 centimeters? Am I still on? Wow, I am barely on. That is crazy. I think I'm going to go for it, but you know what I think I'm going to do, people, is I think I'm going to move my axes slightly upwards so then I can fit this all on the paper. So what that means is I'm once again going to pause this video, and when I come back, to you it'll seem like no time, to me it'll seem like some time, but when I come back, then I'm going to have extended this upwards a little bit and I'm going to have plenty of room to work. One sec. Okay, lovely. Now I have space. So what I'm going to do is I'm going to start by writing my scale. For me, I'm going to have 1 centimeter is equal to 10 meters. Now that might be a good scale for you, but that might not take up your whole page. And so you might want to make this 2 centimeters is equal to 10 meters. Or 4 centimeters is equal to 10 meters. If I had to give a guess, I'd say somewhere either 2 or 4, somewhere in that range is probably going to be a great number for you. Okay. Now that you've done that, the next part is to draw our vectors. We are going to start by drawing vector A. It says a monkey leaves his favorite tree and walks 62 meters due east. Okay. To walk 62 meters due east, we're going to start right here at the tree and go to the east. So I start here at the tree, and I'm going to label my origin as the tree. From there, I'm going to go, I just realized that I made my whole scale wrong, and I really need to be able to have 62 meters this other way, but that was like totally, I mean, we're going to see if this works out. Wow, this is just embarrassing. Okay, let's see. Do I have can I fit 6.2 centimeters this way? I highly doubt it. Let's see. That is 6.2 right there. Wow, I can, miraculously. Okay, here we go. So I'm going to start here at the origin, and I'm going to go from here 6.2 meters this way, and that did not draw at all. So we're going to try it again. Okay, oh gosh, oh hello, what are we doing? Okay, oh gosh, and there's a little dot on the, go. Okay, here we go. Let's keep it peaceful. We start here, and we're going to go 6.2 east, like this. Now, this is very tricky because I am actually, my vector ended right behind the redo button, which is the worst spot for it to land, because now if I try to draw my arrow, can I even do it? Will it even let me? Probably not. Let's see. Okay, it won't let me draw an arrow there, but you get the gist, and you could make it happen. So you would then draw a little arrow there on the end. Next, we are going to label this guy. I'm going to label it A is equal to 62 meters east. After that, he goes 45 meters south. I'm going to change up my color here so that I can draw the next one. When I go 45 meters south, I'm going to start my new vector right at the place where my old vector ended. So that's going to be right there. Is where I'm going to start. We follow the tip to tail. You're going to go from the tip of the first vector is where you're going to place the tail of the second vector. And we're going to go, I'm going to go 4.5 centimeters down. This is already looking really crazy, but we'll see if we can make it better. Did that work okay? Not like too terribly bad. I'm going to say I'm going to keep it. Okay, there we go. Not the best it could be, but not the worst. So then this is my next vector is going to be vector B. Do make sure to keep a little arrow on the end. You'll notice that my arrow was off center there. I'm not satisfied with an off center arrow, so I'm going to do it a little bit better here, and you should do the same because the tip of your arrow should be at the very, very tip of your vector. Next, sorry, I get all like crazy and I like try to clean things up, which I shouldn't even do. That's a waste of our time. Okay, next, I'm going to label this vector, and I'm going to label it vector B. And I'm going to say that vector B is going to be this 45 meters south. So don't forget your vector hat. Don't forget to call it 45 meters. You do need units. And finally, don't forget to say the direction here, which is south. Oh my GOSH. What happened in there? I don't know. Why did we go crazy? Why can't we be normal? We're almost there, folks. Don't even worry. Fret not. We'll write 45 meters south momentarily here. Oh, that was my 5? Come on. Okay. Let's try it again. 45 meters south. Okay. Now, finally, to draw our resultant vector, and this is the hardest part, and I literally do not know if I can do it on this thing. What we are going to do is, first I'm going to change my color. I'm going to go red. And I'm going to start at the origin at his tree, and we are now looking for the displacement. So I'm going to start at the origin. That's right there is my starting point. My ending point is going to be right here. Okay. And now I'm going to draw a line to connect my starting point and my ending point. That was so close to being successful. Do you see how close that was? We're going to take it. Yours would be better, though, because you actually did yours on paper, and you don't have to do this crazy thing that I'm trying to do. Okay. Then we put a little arrow on the end of our resultant vector. Please make sure that those are more connected than mine. And finally, we're going to label it. This is the resultant vector R. And the resultant vector R, if you want to find the length of it, you can measure it. I'll measure mine here, and when I measure mine with my ruler, I get 7.7 centimeters. That translates, according to my scale, I take 7.7, I divide it by 1, and then I multiply it by 10. That gives me 77 meters. So I'm going to write 77 meters, but I am not yet done, because now I have to figure out the angle, and to figure out the angle, I'm going to use my little protractor here. Notice it says we're looking for the displacement with respect to due east. So I'm going to start at east and then make my angle. With respect to due east means I start at the east axis and I'm carving out this angle right here. So that angle, I'm going to take my little protractor, I'm going to put it right along the x-axis here, put my little dot at the origin, then I'm going to measure from the east axis, click, 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 down to right here. And when I measure that on my protractor, starting here, and click, 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 down to here, I get that that is about 36 degrees. And I'm going to label this as theta here, and I'm going to say that it's equal to 36 degrees. Now, I actually need to say which direction this 36 degrees is. So, when I look, I see that I started at the east axis, and then I went south of the east axis. So I'm going to call this 36 degrees. Wait for it, south of east. Oh, I just tried to write with an eraser. Didn't go well for me. 36 degrees. Hang on, the marker is coming back, man. It is on its way. Okay. We are going to go south of east. And then we'll box it up here. But when you box it up, please be careful that you don't box into your own lines. And that is our final answer. That is all for today, folks, for adding vectors using the two-scale method. We talked about what scalars are and what vectors are. Then we did 2 practice problems where we added using the two-scale method. Tomorrow, when we come back, we will be adding vectors together using the math method. Have a wonderful rest of your day, and I'll see you all next time. Bye, good people.